have you ever wondered how your cell phone can detect objects and discriminate between boats and a bridge? Or were you ever surprised when Amazon was able to recommend you a book that you didn't even know that you wanted it? So those are just two examples of what machine learning technology can do for you today. But imagine what it can do in all other areas of our lives. And part of our job at MIT is actually to imagine this future. Here we're working on all different applications of machine learning and AI, ranging from drug discovery, identifying who may be sick, or developing new robotics application, or helping people to live happier and longer. So there are lots and lots of applications out there. But what's so interesting about it, that in terms of algorithms, there is a relatively small toolkit of algorithms that you need to learn to understand how these different applications can work so nicely and be integrated in our daily life. So that's what this class is about, understanding this technology. And I hope that by the end of this class, you would actually know how your cell phone can detect bridges.
Hello, I'm Tommy Akala. I'm a professor here in computer science, and I'm going to be co-teaching this course with Professor Barzilai. I started my career as a theoretical physicist, turned into computational neuroscientist, and now back in computer science. That path sort of reflects the diversity of tools, methods, concepts that are integral to machine learning. So let's talk a little bit more about the structure of the course and the basic layout of machine learning problems. So Professor Barzilai already mentioned that you really need to learn only a few basic machine learning algorithms in order to be able to solve realistic, interesting problems in practice. So let's look at a little bit how these methods are laid out more broadly and how the course is structured accordingly. The biggest piece in terms of setting up tasks for machine learning methods is called supervised learning, and I will use a simple S here for supervised. It is when you're given an example, such as an image, and a target, such as a label that it's a dog, and your task as a machine learning algorithm is to figure out how to produce that label from that image. So in this case, the examples and machine learning methods always learn from examples. So in this case, the example has the correct answer already given. So you're learning essentially in a teacher-student setup. Those are supervised learning tasks. Now there's another piece here which is called an unsupervised learning, and I will use US here as a placeholder for that. Unsupervised learning is essentially a generalization of that when you're no longer given the target exactly what you should do. So think about modeling a language. So the role of the machine learning method now is to try to generate natural language sentences. Or modeling images, its task is to learn based on just observing images to reproduce such natural images or molecules or what have you. Okay? So the major distinction between these two is that here what you need to produce is given explicitly as a target. Here you need to figure out the mechanism of how to generate things. That's unsupervised learning. Now finally, both of these are essentially just making predictions, trying to create examples or predicting what the label might be for an image, what the image is about. The third part is actually acting in the world, and I will use RL for reinforcement learning for short. It is when you're trying to figure out how to act optimally in the world. So it involves making predictions, so it involves aspects of these two, modeling the world, but also it has a goal. It is trying to achieve a certain objective. For example, a robot arm here trying to grasp an object, that can be formulated as a reinforcement learning task, where the method will try to figure out from the failure, it tries things, it may succeed or fail, and based on that, tries to figure out how to do it better. Now, the course here covers essentially the caricature versions of each of these pieces so that you learn the basic components. Much of the interesting stuff here in terms of solving practical problems here happens in the mix of these categories. So the first 3 units in an increasing complexity try to figure out how to solve supervised learning tasks from a very simple linear classification method to more complex neural network algorithms. Here in an unsupervised learning, we talk about probabilistic models, how to generate examples and look at things like a mixture model. Finally, we will introduce you to basic reinforcement learning algorithms, what the problem is, and how to solve such problems. And overall, by learning all of these components, you will actually be able to mix and match these techniques to solve very interesting problems in practice. So in this course, you will see 2 types of lectures. Tablet lectures, where you will see me writing on the tablet and hear my voice, but not actually see my face. You will also see live Blackboard lectures given by Professor Barzilai. And we will alternate different topics given by me and given by Professor Barzilai. Now, this course has 5 units. Unit number 1 focuses on very basic building block of machine learning methods called linear classification. And you will learn a very basic algorithm for solving that problem that will carry on later on, and you can use it to solve much more complicated problems as well. Now, as an illustration and to understand how these methods actually apply in practice, you will also be solving a project. This is like a mini application going through motions that you would have to do if you actually solved a real application problem. So the application in this case is predicting whether an Amazon product review, looking at only the text, whether the review is positive or negative. Now, we expect that there is a little bit of a gap between what we have taught you and what is precisely required to solve this project. So we expect you to think through and try to figure out what type of features to use to feed in to the linear classifier and so on. Hello, this is Machine Learning lecture number 1. Machine learning is already everywhere, so it is a topic that you should know something about. For example, if you type in a search query on the web, how that query is interpreted, how the websites that you're looking for are interpreted, and how the match between the 2 is made. All of this is run by machine learning algorithms. If you look at movie recommendations provided to you, they are provided to you by machine learning algorithms exploiting your previous experience with the site. Going a step further, automated assistants like Amazon Alexa, Google Assistant or Siri, they all run on top of machine learning algorithms. Machine learning is used to interpret speech to natural language, how the natural language itself is interpreted, how it's mapped to content that you're looking for or the commands that you are interested in executing. Machine learning is regularly used for image analysis. For example, in a self-driving vehicle, the unfolding scene coming from camera input is interpreted by machine learning algorithms. Machine learning has also achieved several benchmark tests, for example, surpassing human-level performance in game playing, such as Game of Go recently. Machine learning is being adopted by different disciplines, for example, biology, chemistry, physics, and so on. So it is everywhere, and we need to understand what it is and how to make use of it. So let's start by defining exactly what machine learning is. As a discipline, it aims to design, understand, and apply computer programs that really learn from experience. Okay? There are many ways to learn, or many reasons to learn. You can try to model, understand how things work. You can try to predict about, say, future outcomes, or try to control towards a desired output configuration. We will start by focusing on prediction as a core machine learning task. So let's take a few examples to understand what this actually is. You can make predictions about future events. So for example, you may have a market value of a stock measured as a function of time, and you see some historical behavior of that stock, and you wish to predict what happens the next day. In a similar vein, you can, in a self-driving vehicle, you can try to predict whether a collision is about to happen. In a medical context, you might predict the risk of acquiring or getting a recurrence for a disease, and so on. There are many problems that machine learning algorithms can help you to predict about future events. Now, there are other types of predictions that you can make, not only about events that are about to occur, but about properties you do not yet know. For example, I can take a movie and ask whether you would like this movie. That is a prediction of a property of a movie, whether you like it or not, that I can learn to predict. I can ask about molecules, whether a molecule here is soluble in water or other substance. It is a property that I can learn to predict. I can learn to predict properties about images. What is the content in the image? A category that should be associated with the image, that it's about mushrooms. In a more structured way, I can also turn machine translation into this form. I can take a sentence in English and ask, what is the corresponding sentence in Spanish? Now, common to all of these tasks is that A, we can learn to solve them, but B, they would be very hard to solve in a traditional engineering way, where we specify rules or solutions directly to this problem. How do I specify the solution to the problem of whether you like this movie or not? This is much easier to learn from experience. Let's be a little bit more concrete. So the machine learning tasks are really provided in terms of examples. It's very easy to show examples of how you would want the method to behave. Examples of correct behavior. I can take an image, I can provide an annotated category for that image, what I want the method to predict, another image, corresponding category, and so on, and now generate a large set of examples that illustrates what the task is. This is typically very easy to do. Okay? I don't have to specify the solution to be able to illustrate the task implicitly through examples. The power of machine learning really is now in terms of automating the process of finding the solution to a task that's illustrated by examples. Okay? So what we do is we hypothesize a set of possible mappings, a large set that takes an image and produce a category as an answer. What that mapping is specified by parameters. A different value for these parameters will specify a different mapping. And I would like to find out of the possible parameters the one that agrees with my set of examples the best. We will automate this process of finding these parameters and also specifying what the mappings are. So this is what the machine learning algorithms do for you. You can apply the same approach in different contexts. For example, in machine translation, you can easily specify what the task is by giving an English sentence and a corresponding Spanish sentence and have a large number of them to illustrate what the task is. Then specify a complex mapping that can take a sentence as an input, has some adjustable parameters that specify different possible mappings, each parameter value providing a possible answer that may or may not agree with the correct one. And we search for those parameter values in an automated way in order to find the best mapping for this task. Google Translate already operates in this mode. Now let's take a very concrete example of how to specify a machine learning task and how to solve it. Let's consider a movie recommender problem. I have a set of movies I've already seen, and I wish to use the experience from those movies to make recommendations of whether I would like to see tens of thousands of other movies. First thing to do is to illustrate the task for the learning algorithm. So I need to annotate here 4 possible movies that I've already seen. Fury, it was too violent, I gave it -1. Gone Girl, too sad, -1. And everything that has to do with science fiction, I will give +1. So now I have 4 annotated examples that illustrate the task that I wish to solve, how to recommend movies for me. The real task, though, is to recommend correctly movies out of those tens of thousands of unseen movies. Okay, there's here a discrepancy between the information available to the algorithm and the task that it wishes to solve, which is the recommending the future examples that I wish to do accurately. We will get back to that point. Now, the first step here is that while the computer can easily understand the +-1 labels that I've annotated the movies with, it doesn't really understand anything about the movies. So I need to construct a feature vector, put the movies into a form that the computers can understand. We will compile a feature vector for each movie systematically so that we can add that procedure, apply that procedure to each of the movies in my little training set here, set of examples that I have already seen, as well as to any of the future examples. So how do we construct the feature vectors? X here is a vector, 1 here, superscript 1 denotes the identity of the movie in the set of examples that I have, 1, 2, 3, and 4. Now, I will construct this feature vector by asking questions about those movies. For example, I can ask whether it's an action movie and give a binary answer 0, 1. It is an action movie, so I give it 1. Is it a comedy? No, so I give it a 0, and so on. I can construct many such questions, apply them systematically to that movie, and as a result get a binary vector associated with the movie Fury. Now I can apply the same procedure, same set of questions in the same order to the other movie, Gone Girl, and construct a feature vector corresponding to that movie. Okay? I can also apply the same procedure for all of the future movies that I encounter, and thereby hopefully make a recommendation for whether I would want to see them or not. All right? So at this point, what we have is a training set of examples, vectors with the associated labels. These are in the form that computer can now understand. Its task is to learn a mapping from those vectors to the labels. It's called a classifier, as we will see later on. Now, in machine learning tasks, the key distinguishing part here is between the training set, which are the annotated examples that I'm using to illustrate the tasks for the method, and test examples that are not yet available to me. I have the training set, but I really wish to solve the task over the test set. It is this discrepancy that makes the learning task interesting. I wish to generalize what I extract from the training set and apply that information to the test set. So I wish to learn the mapping from examples X to labels plus minus 1 on the basis of the training set, and hope and guarantee that that mapping, if applied now in the same way to the test examples, it would work well. That is the task that I wish to solve. Now let's look at this a little bit more geometrically. Those examples, X, here I have X1 represented as a point in space. Its vector has a representation as a point in space, and I can now place all the 4 training examples as points in this space. Just to facilitate the illustration here, I've assumed that the coordinates of those vectors, the first 2 coordinates, are actually real numbers rather than binary numbers, so that these examples are a little bit more scattered. Okay? Associated with these examples are also the labels. So we denote them with Y's, the label. The label associated with the first training example is -1. Okay? Now I've kept here the covers of the movies, but that's not really necessary. The only thing that the algorithm sees are these points in space here, X1 and Y1, the associated label. This pair is one training example. Okay? The training set as a whole is now a set. We will denote it as S, subscript N. Here N is 4. We have 4 training examples. It is a collection of pairs of those vectors. Now here in R2, in my illustration, each vector has 2 coordinates. Ith training input vector here, feature vector, has an associated label that's in ±1. And I have N of those pairs, where N is 2 here, N is 4 here, and that is my training set. Okay, so training set here is a set of example that includes the feature vector and the corresponding label. Now, this is all the information that's provided to the learning algorithm. But the task that I would really wish to solve is the one that corresponds to the test examples. So each example here is also a pair of a vector, feature vector, associated with the label. But I don't know the label. The label is unknown until I actually see and view the movie, and then I know whether I would have wanted to see it or not. Okay? But the task that I wish to solve is to correctly label these question marks here associated with the future movies, rather than the training examples for which I already knew the labels. Okay? So what we have here for the learning algorithm, it doesn't see the test examples, it only sees the training examples. Okay, so on the basis of these 4 training examples, pairs of feature vector associated with the label, I need to learn to map each example, each x here, feature vector. So each point in this space, R2 here, I need to learn to map that to a corresponding label, which is a plus minus 1 label. So each point has either plus 1 or minus 1 associated with it. What we need is a classifier, that mapping from points to corresponding labels. So each classifier here maps the space where the examples live, here again R2, to the corresponding labels Y that live in plus minus 1 labels. Okay, so each X here, I can apply the classifier to that point and get an answer, for example, 1. If I took a different point and applied the classifier, I might get minus 1. So what the classifier does is divide the space into essentially 2 halves. One that's labeled 1 and the other one that's labeled minus 1. Let's take a few examples. Here's a classifier known as a linear classifier because it divides the space linearly into 2 halves. It has a part of the space where all the examples here are mapped to plus 1 and all the examples in the other half are mapped to minus 1. This is one possible classifier that we could use to take a point in this space and map it to labels. Now, it does not agree well with the training examples that I have because it misclassifies this as a negative one and it misclassifies this as a positive one. So according to the classifier, this one would be a positively labeled movie. Okay, so we need to now somehow evaluate how good the classifier is in relation to the training examples that we have. To this end, we define something called training error. So capital E is the error. It has subscript n that refers to the number of training examples that I have. And I apply it to a particular classifier. I evaluate a particular classifier in relation to the training examples that I have. Okay, how do I do that? Well, I take the classifier, apply it to the ith training examples. As a result, I will get plus minus 1 label. I compare that with the given label for that example. Okay. If it's not the same, this statement here is true, so there's a discrepancy. Now I use here double brackets here denote a function that takes a truth value inside and returns 1 or 0 accordingly. Okay, so when I compare what the classifier produces with the correct label, if they are distinct, what comes out of here is 1 if there is an error. If the classifier makes an error on the ith training example, and 0 otherwise. Okay. Now I want an error on the whole training set, so I sum this over all the training examples, n of them, and take a fraction. So what I get here is now a fraction of errors on the training set. also known as the training error. Okay, now I can use that to evaluate how good my choice of the classifier is on the training set relative to the training set. Okay, so this is a bad classifier according to this. The fraction of errors, it misclassifies half of the examples, so the training error of this classifier would be exactly 1/2. So we would say that this is a chance behavior. It doesn't do any better than coin flipping on the training set. Okay, here's another linear classifier, a different mapping that maps these examples here to +1, these examples here to -1, and it seems to correctly classify all the training examples. So as a result, the training error of this classifier, training error applied to the classifier, we do the same, take the fraction of training examples that are misclassified, that is 0, the training error is 0. So according to just the training examples, this seems like a good classifier. Okay. Now let's illustrate the difficulty in the machine learning task. If we only considered linear classifiers, maybe the choice is now clear. We would choose this as the classifier. Okay, and might have reasonable guarantees that that we will also show later that we would do well on future examples, those test set examples that we have not yet seen. The task is a little bit more difficult. Consider here another classifier that we could choose. Classifier is any mapping that takes as an input the feature vector and provides a ±1 label. Okay, so for example, this is a classifier. It correctly classifies all the training samples. The shaded regions here correspond to classifier returning +1 and the rest -1. Okay, so all the training samples are correctly classified. The training error of this classifier is also 0. Let's take a more extreme example. Here's a classifier where the shaded regions are just wrapped around those positive training examples, and all the rest are classified as negative. Okay, the training error of this classifier is also 0. Okay, the problem here is that if we consider now the test examples that we wish to classify correctly with this classifier, all of those test examples that are not exactly the two positive training examples are classified as negative. So if about half of the test examples have positive label, about half negative label, this classifier would have a test error about half. So it would be a chance level performance for test examples, even though it perfectly classifies the training examples. So what is going on here is an issue called generalization. How well the classifier that we train on the training set generalizes or applies correctly, similarly to the test examples as well. This is at the heart of machine learning problems, the ability to generalize from the training set to the test set. And the problem here is that in allowing these kind of classifiers that wrap themselves just around the examples, we are making the hypothesis class, the set of possible classifiers that we are considering, too large. We improve generalization, we generalize well, when we only have a very limited set of classifiers, and out of those, we can find one that works well on the training set. Put another way, the number of choices that we have available when we consider fitting to the training set is the complexity of the set of classifiers, and it actually runs counter to generalization. The more complex set of classifiers we consider, the less well we are likely to generalize. Okay? So we wish to, in general, solve these problems by finding a small set of possibilities that work well on the training set so as to generalize well on the test set. We will talk much more about this problem of generalization later. All right, let's take a step back and look at things more broadly. There are many types of supervised learning problems, as we illustrated. Supervised learning task is one where you are specified the correct behavior, examples of a feature vector, and what you want it to be associated with. So you give supervision of what the correct behavior is. You can generalize now from a binary classification +-1 to multi-way classification. So the answers that you use are categories more than 2. You can solve regression problems where the outcome that you wish to associate with the input example is a real number rather than a category. You can generalize this further so that the output itself is a structured object. You can take an image and predict a sentence that's associated with the image, such as a description of the image. Okay? Machine translation would take a sentence as an input, and the output would be the corresponding sentence in another language. There are many other types of machine learning tasks, some of which you will learn in this course. Supervised learning is one where you explicitly specify the correct behavior, as we've seen so far. Unsupervised learning, strip the labels. You are only given the examples. You can observe, but the task itself is not well defined. The problem there is to model, find the regularities in how those examples vary. That's an unsupervised learning problem. Semi-supervised learning is a mix of supervised and unsupervised. Active learning is a problem where the algorithm can itself ask for useful additional examples. If it would think that knowing the answers to these examples would actually help it learn better, it can actively solicit additional information. Transfer learning is a task where you train the method based on one scenario and you wish to apply the method in a different scenario. For example, you may wish to solve the machine translation from English to Spanish and wish to apply the method to a translation task from English to Portuguese. How we could make that transfer is a transfer learning problem. Reinforcement learning is a problem of learning to control, learning to take actions in the world so as to optimize some criteria, like how a robot can grasp an object where the outcome that you wish to maximize is a successful grasp by the robot. And the actions available to you are the joint torques that you can exert on the robot arm, and so on. So let's recap. The important things that you should take out of this lecture are posing supervised machine learning tasks in terms of examples, understand binary +-1 supervised classification problem, what is a classifier, the role of training and test set, that the training set is illustration of the task, test set is what we wish to really do well on, but those are examples that we don't have available at the time we need to select the mapping. Classifier is the mapping that we wish to learn from the training set. A set of classifiers is the set of alternatives that we consider when we see the training set and pick out of that set the best fitting classifier. Errors, we talked about training error, and we talked about generalization, how we can do well on the test set.